Good afternoon, everyone. Thank you for joining us for this third instance of the UAS webinars brought to you by the Frontier Precision UAS team. My name is Phil Johns, and I'll be taking you through this webinar with some of my colleagues today. As I stated, this webinar is the third in a series. The last couple of weeks have been great. We started on April 9th with choosing the best tool for the job. We followed that up last week with Mike Clarenbeek and myself with UAS for inspections. Today we're going to dive into photogrammetry and where we're at, where it came from, and whatnot. Joined today by a number of the members of my team. Really all the members of my team are here today in full force. And Chris Rice is a UAS specialist from Boise. How you doing today, Chris?
Good. Thanks for having me.
Yeah. We got Chris Kelly, who is our representative UAS specialist out of Seattle, Washington. How's it going, Chris?
Doing good, Phil. Thanks for having me on.
Yeah, man. Nathan Stevenson is our AGE, our Applied Geospatial Engineer, resident LiDAR expert, and all things photogrammetry expert. Nathan, how's it going today, man?
Good. Thanks a lot, Phil. Happy to be here.
And finally, with our full house, we have Mike Clarenbeek, who also joined us last week and headed up the UAS inspections. He's one of our public safety specialists out of Sioux Falls, as well as just in general expert on all things drones. How's it going, Mike?
Hey, Phil. Good. Thanks, guys, for having me at another webinar. Looking forward to it.
All right, so what's cool about this webinar today is everybody is going to be pretty involved. It's been a handful of us on each one today. We're going to have case studies brought to you by Chris Rice, by Chris Kelly, and Mike Clarenbeek. Nathan, as always, will be our expert answering questions for you in the background. And I'll be here sort of heading up the primary beginning and bulk of the photogrammetry webinar. So Frontier Precision is a national dealer for a number of UAS manufacturers. As you can see here, we don't need to go through all of them, but just kind of the idea here is that by being a dealer for not just one or two or a specific instance of software or hardware, it really opens up with the ability to just offer the best solution to our customers and really kind of compare and contrast each of those technologies and recommend what we feel, in our experience, is the best. Frontier Precision as a whole has 12 offices in 11 states. We cover those states and some of the surrounding states as a Trimble geospatial dealer. But as I mentioned with those manufacturers that we pictured or showed in the last slide, we are a national dealer, so no limitations there. All right, so this is what we're here for, UAS aerial photogrammetry. All right, so today we're going to cover a broad array of topics. I'm going to get into the history, as I always like to do, kind of see where we came from, nerd out a little bit on that. We'll dive into the fundamentals of aerial photogrammetry using UAS, sort of the concepts and procedures. We'll talk about data processing, both locally and in the cloud. Same technique, just in different applications. Then we'll actually talk about or just review a couple of the applications that we talked about originally in that getting started, choosing the best tool for the job, review a little bit of that. And then we'll have our guys cover some case studies, actual field applications of the technology and the equipment and the techniques that we used for these specific situations with our customers. All right, so photogrammetry. By the definition of the American Society of Photogrammetry and Remote Sensing, it is the science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, interpreting photographic images and patterns of electromagnetic radiant imagery and other phenomena. Basically, it's the science of making measurements from photographs. Photogrammetry is derived from the word photogrammetria. It's a Greek word that is made up of three other Greek words, phos or phot, meaning light, gramma, which actually means drawn, And then metrion, which is the noun of measure. So not the verb or measuring, but the measure of something, the noun of measure. When we talk about photogrammetry, we really want to start with perspective. Perspective defined is the technique or process of representing on a plane or curved surface the spatial relation of objects as they might appear to the eye. It's your point of view. It's looking at something and seeing as the human eye would see it. Just to dive into the history a little bit, we'll start with Filippo Brunelleschi. He observed that parallel lines seem to converge at a single point in the distance. This is pretty commonplace, even in elementary when you're starting to talk about perspective, but back then this was just something that didn't exist. So he developed a way of mathematically calculating scale and making things appear as real life appeared. Paintings, before this time, the individuals were the same size, or distorted in unusual ways. So this is really the turn of where we started to see in art perspective taking place. All right, next, one of Leonardo da Vinci's contemporaries, Leon Battista Alberti. He released a treatise called Della Pictura, which means on painting. Continuing this perspective theory of a single point came to be known as a vanishing point on a horizon line. Then we'll dive into my favorite individual probably throughout history, or at least top few, Leonardo da Vinci, where we use his applications, his perspective drawing and projective geometry. I thought this is a pretty cool quote here. Perspective is nothing else than seeing of an object behind a sheet of glass, smooth and quite transparent on the surface of which all things may be marked that are behind this glass. All things transmit their images to the eye by pyramidal lines, and these pyramids are cut by the said glass. The nearer to the eye these are intersected, the smaller the image of their cause will appear. This kind of thought and outlook is really what defined art going forward, and really how we looked at that art to develop perspective and eventually photogrammetry. This is a drawing of his from 1480 of the perspectograph. This is a study of one of his famous paintings, Adoration of the Magi, where he actually broke down what he was using, the horizon line, all of the perspective features to show scientifically what he was doing there. Last Supper, 1495. Very heavy use mathematically of what was going on. You can really see the geometry of what he's doing here with horizon. After that, we're going to move on to Albrecht Dürer. And Albrecht created a book called Das Künstlerhandbuch, that is the artist handbook. And what he did in there in 1525 is basically defined the laws of perspective. He created an instrument. I think he called it the perspective machine. This is an etching of his that he did to show this machine. It's titled Man Drawing a Lute. And it just basically shows a string going from the wall through the area that he's looking at on the section. And he's reflecting that image down onto another surface, creating dots or outlines of that image for later reference in drawing for perspective. So pretty cool stuff there. Johann Lambert, Perspectiva Liber, the free perspective. What he did is he was able to find mathematically the point in space from which the picture was made. The point in space we have point A here, and then he derived the actual perspective of where the camera was at for that photograph mathematically, using a technique called space resection. All right, we move on to Francois Arago, and really this is the first use of photogrammetry using a previously developed process by Daguerre called the daguerreotype. And this is where we really start to see the turn heading towards modern photography and photogrammetry. Aimé Laussedat, the father of photogrammetry. This is the first person to use multiple terrestrial photographs to compile a topographic map. And then we have Nadar. That's his nickname. His real name was Gaspard Philippe Cornachon. He's a French photographer and balloonist known for taking the very first aerial photograph. Many of these photographs actually have not survived. While nadir does come from the Arabic word for opposite, he's generally given credit as he is known as taking the first aerial photography. So now we use this term nadir for above or straight over our subject. This is the earliest surviving aerial image taken above Paris from roughly 250 feet or so in about 1866. He actually gained the patent on the utilization of aerial photographs in map making and surveying. However, it took him about 3 years before he was able to take this photograph or other photographs. And one of the reasons is because they were using the collodion photographic process at that time, essentially having to put a dark room in a balloon. By no means a small achievement. And so from there, we want to get into an idea developed by Gottfried Konecki in 1985. And basically, the idea is that the developments of photogrammetry, the 4 generations, have followed major developments in technology. So the cycles that include the first generation started in and around 1850, and each of these cycles lasted about 50 years. The first generation, mostly pioneering and experimental phase, with the terrestrial photogrammetry and the balloon photography and photogrammetry that we talked about just then. The second generation is usually referred to as the analog photogrammetry generation. And it's really characterized by the invention of stereo photogrammetry around 1901. The first instance of that was the stereo comparator in 1901 by Karl Pulfrich. And then the stereo autograph by Edward von Orell in 1907. All right, by the time we get to World War I, we're really starting to see aerial photography take place. Many of these techniques that were developed for aerial surveying that were built between World War I and World War II, flying at a particular constant speed, using nadir imagery at a fixed focal length, things that we'll talk about coming up here. They really still stand the test of time and are used today. All right. If we jump back to the timeline here, when we see the invention of the computer around 1950, we move into the analytical photogrammetry phase. This is where they really started to use matrix algebra for the first time, and the first real attempt made to employ adjustment theory. And this is basically correction of the location or position of these photogrammetric measurements. By the time we got to the 60s, accuracy, based on the programs that were being created, we've really increased aerial triangulation accuracy by a factor of 10 or more. So we're really seeing giant jumps in that improvement. One of those improvements that we saw was with this invention. This is what's known as an analytical plotter. When this was introduced right around the late 50s, we really didn't see it available on a broad base until the 70s. All right, and then we get to digital photogrammetry. So obviously the past 30 years, digital photogrammetry has changed. We were talking about the advancements in what we're doing today. We've just really advanced our method of processing and the graphic interface that we do that on, as well as the abilities of those individual systems. All right, so now we're going to go into fundamentals. Let's get into what we're really here for. So UAS photogrammetry, a little bit of a review on what we talked about before, but one of the reasons we really like it, we've taken it from the plane, but where the benefit comes in when we integrate it with UAS is it's very versatile. We can get it rapidly deployed. We're not having to go take off at an airport. Can get very high resolution. We have a number of payload options. And in the grand scheme of things, comparatively, it is extremely affordable. Some of the modern camera payloads that we're used to seeing here, RGB is the most commonly used one. Now we're even getting into medium format, which was primarily used in just airplane photogrammetry, but now companies like Phase 1 Industrial is releasing pretty groundbreaking sensors. This one is the IXM100 that's 100 megapixels. Overkill for many situations, but really opening up the abilities of what we can do in others. FLIR thermal for beyond the visual spectrum. getting infrared thermal photography, and then even breaking up those different frequencies of light into multispectral imagery. So the Altum that you're seeing right here is really breaking it down and capturing the red spectrum, the green spectrum, the blue spectrum, the near infrared spectrum, and the infrared long range spectrum, all in one single package. A lot of times this is used in agriculture applications, just because when we break up those different spectrums, we can see things that we generally would not see when the spectrums are just kind of folded in together in a single image. All right, so if we talk about actual fundamentals themselves of photogrammetry, we're using some sort of aircraft or satellite. We primarily here are using UAS to photograph the Earth. That camera system, as we spoke before, is in a nadir or nadir position, so it's facing downwards. That is not the limitation. There are many leaps and bounds in how oblique or pointing at more of an angle can actually enhance the 3D modeling that we're getting out of photogrammetry. We're not going to talk about that too much today, but I just want you to know that nadir is not the only, but it is, premier function that we use. And we're GPS enabled. Now that we have global positioning, we want to know, hey, where are these images at? So we have a rough idea of where the images are taken from, and then we use points on the ground to further correct and stitch these images together with tie points. All right, so farther into the fundamentals, we'll start with the image itself. When we look at the single image that we take, we're looking first to identify a principal point position. Very simply, it's just the center of the image. This is where lat, long, and elevation data is created and tagged in that metadata, or what we call EXIF data. When multiple images are stitched together to create a mosaic, no different than an artist's mosaic with multiple pieces of glass, we're using multiple images. Basically, the average of the principal point data in that image places or locates georeferences, we call it, within that model that we're creating on the Earth. All right, so image overlap. This is how we actually capture these images. So at a specific setting, we identify prior to flight. Depending on the features being mapped, we're going to set two different functions: forward overlap and lateral overlap, or just known as side lap. So frontal or forward overlap, or side lap, lateral overlap. Basically, this ensures that there's enough images when we get on the ground and we're ready to process this to effectively stitch all of these together and make one congruent solid map. Because we are defining the lines that we are actually flying and the amount of pictures we are actually taking, this is going to affect flight times, not only in UAS, but in any aerial photogrammetry application. All right, another concept here that we want to deal with is ground sampling distance. So what you're seeing right here on the left is basically an image really zoomed in to a single pixel. And so the ground sampling distance, or what we call the GSD, is the average resolution of those images that we are taking. And very simply, we are using a fixed focal length. We don't want to be changing the focal length as we're flying. We want each image to be very, very similar, both in exposure and focal length. So we are simply adjusting this by our flight altitude. And so the closer we are to the ground, we're going to have a lower centimeter per pixel. So let's say 1 centimeter per pixel is a very high ground sample distance. And that's going to give us much better data integrity. If we have a lower GSD, or really a higher centimeter per pixel, so let's say 5 centimeters per pixel, I mean, each pixel in that photograph is 5 centimeters wide or tall, or however you want to say it. When it says more processing error, I mean, the idea is that if we can't see what's in the imagery, we can't define and make measurements from that imagery. So this really dictates our average horizontal and vertical accuracy. So if we have a fixed focal length, the Earth is not flat, contrary to fairly unpopular belief. We want to follow that terrain if at all possible. This isn't such a big deal if we maybe have 20 or 30 feet of change in our elevation. But if we're flying, like we do out here in Colorado in the mountain ranges, or just in an area where there's a lot of elevation changes, we really want to maintain the most consistent GSD, or ground sample distance, possible. And so the way that we can do that is through our flight planning software to enable downloading either SRTM data from the USGS that's free and publicly available, or we can even import our own DM from a previous survey that we've done to derive that flight altitude. Okay, so let's talk about positioning and correction. If you joined us on our first webinar, this is pretty much review. For that reason, I'm not going to spend too much time on it, but I just wanted to do a quick review. How do we correct the location of these images? Very, very important. Traditional GPS generally has an accuracy between about 1 meter and 5 meters, meaning if I am in location A and my camera says this is where I am because the GPS receiver told me, it could be anywhere from 3 to 15 or so feet away from that point and still be like, yep, I'm good. I'm exactly where I should be. For this reason, we cannot rely on lower end or consumer GPS modules to correct that imagery. You've experienced this probably if you've ever gone to maps in your phone and the blue dot showing somewhere far off from where you actually are, and it might even move or jump around and maybe get a little closer to where you actually are over time. And so this concept is consistent across all GPS. So one of the methods, or the most common method that has been used throughout history if we averaged, is probably ground control points. This is not only in traditional surveying, but in aerial photogrammetry and aerial surveying as well. Essentially, the concept is we have a base station. It sits there and quote unquote what we call cooks or collects location data from the constellation of satellites. And over a period of time, it gets more and more accurate knowing where it is. We generally will leave a base station for at least over 2 hours. And then the concept of a rover, which was introduced, not too short ago, a while ago in surveying, would be that we would use this relative correction rover based on the known location of that base station. So whereas in traditional static surveying, they really had to just let that point sit there for a very long time, then go let it sit somewhere else for a very long time. When we brought in RTK positioning with a rover, it allowed us to reference that base station and correct that rover's location in anywhere between 20 seconds and 2 minutes. So huge improvement using something called real-time kinematics. So we utilize that base station and rover to set these known points, and we call these ground control points. These ground control points essentially are a point on the Earth that we absolutely know with a fair amount of certainty that this is where this point is. And then what we do is we lay a very large target that's visible from the air. These essentially used to be really large with airplanes. They're getting smaller and smaller with UAVs. But when we do our survey, we have these ground control points laid out. And then when we process, we can utilize those points to correct the position of the photographs themselves. So we're not relying on the GPS of the photograph. We're now looking, we're almost throwing that away essentially and looking at these ground control points to say this point in this photo is this place on the Earth. And if we have them spread out, pretty evenly across the site, generally about every 1,000 feet or so minimum, we basically can correct that imagery with very good confidence that it is an actual place on the Earth. So this technique really yields the highest accuracy. The issue is when we get into laying ground control points, here's an example of a couple hundred acres, 8 GCPs. Generally 100 to 200 acres, 7 to 8 GCPs is probably fine. But when we're using the same methodology and we jump up to 3,300 acres, this is another job that I showed a customer, like this is why we use a different technology. Using that same methodology, 720 GCPs, insane, crazy amount of time, and we start to look for something else between accuracy and convenience. Can we get enough accuracy with a little more convenience? And so that moves us into our next stage here. In the surveying world, what I mentioned, RTK, it's that reference correction based on that base station's location. The issue here is that when we're using a rover, it's required to have a link to that base station. If at any time when you try to collect that point on that rover, if it does not have link to that base station, you cannot get that point because you don't have your reference. Now, in traditional surveying, if you're walking around with a rover, not a huge deal. move away from a tree, move away from a building, collect a point somewhere else, wait a few minutes to get that link back, collect that point. However, when we move into the world of drones, the drone is the rover. So in RTK, what we were very, very excited about when it hit the world of drones, we became a little less excited in situations where we might lose that link. And so RTK, while it is still a very functional correction method for drones in many situations, really the most reliable way of correcting drone imagery is through a process called PPK, or post-processing kinematics. The difference here is that we still have to have a base station, we still have a rover, which is the drone, but we do not have to have a connection between the base station and the rover or the drone. We simply collect logs on both, and then in post-processing software, we actually correct that imagery later on. All right, so as I mentioned before, PPK, RTK in our previous presentation, it's pretty much every single manufacturer, major manufacturer. These are some of the ones that we carry, DJI with the Phantom 4 RTK and the M210 RTK, Del Air with their UX11 PPK, and then Quantum Systems with their Trinity PPK and their Tron, which also uses PPK. And also has a capability of another technology that I'll talk about, which is precise point positioning, or PPP. So PPP actually introduces, in addition to the full constellation GPS, GLONASS, Galileo, and Beidou satellites, the most advanced technology we have in satellite positioning, which is our geostationary L-band communication satellites. Coupled with reference stations in the locale that you are flying at, along with doing precise satellite orbit and clock corrections. So we're not actually processing in real time with RTK and our own base station. We're not taking data from a base station and our rover and processing it post. We are actually relying on the location and correction of these L-band satellites to, in real time, correct that information very, very precisely. And then we move into being able to do this also with drones. There are companies now, Trimble with their acquisition of a Planet. They have, this is what you're seeing is the APX-20. It's used in yellow scan LiDAR. It's actually used in the phase 1 industrial setups that I showed you earlier. Micro drone systems that we sell actually have this. The Del Air, not the UX11, but some of their larger LiDAR units actually use this. And then these are for manufacturers, for OEM drones to install. And then we have Cloud Geomatics, definitely a company that we're very excited about and utilizing ourselves and kind of putting it through the paces. But the idea here is that this is a modular system. It supports PPK processing. If you attach it to pretty much any non-PPK RTK drone out there, it enables it for PPK. So things like even the Phantom 4 Pro, you can put this guy on there and now have a very capable mapping surveying drone. You can attach this to, we have it attached to an M200. Very exciting stuff, and we're happy to answer more questions about that if you guys have any questions going forward. All right, so let's talk about data processing a little bit. Kind of two different options. There's desktop applications and there's cloud applications. These are some of the options for photogrammetry processing software. There are others out there. There's actually quite a few. Pix4D, it just happens to be the beast that everybody knows about. Metashape, not a new kid on the block, but one we're very excited about in terms of getting very clean point clouds and just really clean, accurate data. Bentley, very well known for vertical construction, 3D modeling. So utilizing some of those techniques, nadir in addition to oblique imagery, Bentley does that very well. And so when we talk about photogrammetry processing, getting that software, local processing is what most people know about and what most people have used. When we talk about Pix4D, you're going out, you're getting a computer, you're getting a software license, you're getting your training, and then you're off and running. Fairly good. Photogrammetry is not a simple art or science, but programs like Pix4D make it very accessible. And with a bit of training, which we also do here at Frontier, you can be off and running in a fair amount of time. I would say probably at expert level in a couple of years. Cloud processing is a newer kid on the block than local processing. Really has started to take place in the past 10 years or so with companies like Airware and Drone Deploy, Propeller, also known as Trimble Stratus. These companies are really pushing the envelope on cloud processing. And so we'll talk about and compare just for a moment here these two. So with local processing, it's kind of choose your own adventure and go with it. You're not choosing and then choosing again or buying both. The reason for that is the software is fairly expensive. Pix4D is about $5,000, Metashape is about $7,000. I'm not sure the current price on Bentley. Whereas with cloud processing, a company that we carry, which is Del Air, really exciting technology there. They acquired the Airware assets a couple years ago. And what they do is actually put the Metashape, Pix4D, and Bentley context capture engines under one roof. And it's a pay-to-play methodology where you can choose which engine you want to use on a job-to-job basis. So pretty exciting. And whether you're going for local processing eventually or not, it's a very good option as either a backup for scaling or to try out these different engines with a handful of credits and see which one works best for you. Photogrammetry processing, as far as local goes, control over the entire process. We do not require an internet connection. Sometimes that's important, whether for security reasons or for just access locale-wise. Many mines, if you're out in the middle of nowhere, internet's just not an option. However, these workstations are very high cost. And this high cost does not only go with the workstation, but also the software license and extensive training. Again, it does have its benefits, and we're happy to kind of break those down at a deeper level if you want to reach out, but this is kind of a high-level summary. With cloud processing, really the difference is, originally cloud processing was what's known as sort of a black box. You kind of uploaded your data and hoped for the best. What you get back is what you get back. We don't live in that world anymore. Companies like Del Air and other companies of the like really have made great advancements over the past few years where you collect the data, you can lay your control, upload that control, and tag it yourself in the cloud, similar to how you would do on a local processing machine. Even if there's a processing error or an issue, they actually have individuals download that data, reprocess it, check for accuracy, communicate with the customer on ways to improve that. So really it's a back and forth relationship rather than just sort of putting it in a black box and hoping for the best. It does require good internet because you have to upload all that data. However, when compared with local processing, you don't really need a license at all. It's credit-based, or they even have unlimited. Del Air is basically $12,000 for unlimited processing. You could process a data set every single day, every day for a year, and you can still keep going. Other companies such as Propeller is about double that cost, but generally from 12 to 20, 25K per year. But keep in mind, while that may seem expensive compared to local processing, if we start to compare these, it's just really not. When we talk about human hours, paying an individual, what it takes to employ that individual, the software license itself, the workstation, that probably is going to need to be replaced every few years. We did a little layout here and showed, if we did one data set per week for 52 weeks for 1 year, average of 8 hours a data set, might be a little more, might be a little less. It's probably going to be more when you first start out, may get a little better as you move forward. But what we really start to see is the savings being shown. So, I even threw the internet cost in there for $1,200 to try to put every single thing I could in there. Unlimited processing, again, you could process 365 or how many ever data sets you want a year for that price. But for comparison purposes, we just took the upload of roughly a half hour, probably even less once you get going on it, maybe 5 minutes, 10 minutes of man hours. And so even just with those sort of curves, we're seeing it's about half the cost. And you don't need to know photogrammetry. You don't need to learn the science of photogrammetry. If you're a surveyor, you can survey, you can verify with checkpoints, you can do everything you're used to doing with your own surveys, but without learning photogrammetry. So pretty exciting option there with cloud processing. So application-wise, aerial photogrammetry applications, a couple here. We've talked about a number over the past few weeks, and we'll get into a couple here right now with our case studies. Here's a few: geospatial, getting that high resolution imagery, vector data, 3D mapping, multispectral imaging, if you want to use that sensor for vegetation and agriculture analysis. Engineering is probably the most wide use, and this could be any, this is really just surface modeling. So this could be construction, mining, surveying, mapping. This is really the photogrammetry, pulling the measurements out of that data we're getting. And then we're even seeing instances in public safety, huge uptake in public safety. Most police departments now have a drone in their repertoire, if not very actively looking at it and testing it. So I'm going to go ahead and jump over to our case studies. So Chris Rice, if you want to maybe talk about what you did here on the Feedlot hydrology modeling, go ahead and take over.
So I wanted to focus on a case study that I did, or actually a job that I did here in Idaho. This was a situation where we had a little bit of runoff problems. Obviously, feedlots are susceptible to this. And of course, as you can see in this image here on the left, this is from Google Earth. You can see obviously there's a big hillside, and then you can see runoff happening. The Snake River, which runs through this valley, is not too far away. So this required a pretty extensive hydrology study to see what those potential impacts were. And so a land surveyor actually approached me and said, hey, I need to actually physically model this entire 230 acres. And I said, well, yeah, you usually do that, using a traditional survey method. So I said, well, hey, let's use the drone instead. It's a perfect example of an area where we can do that because there isn't a lot of trees and other things getting in the way. So, we're able to actually get down to bare earth and do the modeling very well. So I said, okay, I know you guys are pretty particular about absolute accuracy. So I said, what is it? Do we actually need less than 2 centimeters, or can we get away with a little more? And so the 3/10 mark, which is 3/10 of a foot, that's about 3.6 inches. That was sort of the meter of this. Bam, we're perfect. So we went ahead and got it all together. And if you could flip the next slide for me, Phil, that'd be great. Am I supposed to do that? Sorry, guys. Thank you. Okay.
Technical difficulty.
Some of you might be in the surveying industry or do this or work with surveyors. You understand that a traditional survey method is usually what we could see here. You set up a base, you have a rover, and you go around and you mark positions. You get elevation. Usually you're going to mark other features as well, so that when you go actually do the design work, you can go in and create these features. So the purpose of this exercise was to basically look at the comparison. And so the traditional method that was going to be employed on this particular job was we were looking at a 40-foot grid, and over 230 acres, that's about 21,000 total spots, right? So that's quite an endeavor. The purpose of this was to be brought into AutoCAD Civil 3D and then digitize these features so that this hydrology study could be carried out. It's an extremely exhaustive method, but it's highly accurate. But again, it's very time consuming. So if you have to turn around a deliverable doing this, it might take weeks versus days. And then the final bullet is an important one. Because you're using imagery to do the digitizing, you might not have an up-to-date source. So that's where the drone data really comes in and helps. Next slide, please. So alternative to traditional survey, we went ahead and we got the green light to fly the drone. So in the 5 steps here, this is how this all worked out. The first step was to set up a base. So we were able to get a Rhinex file off of that base. So we did a 1-hour cook before flight and then a 1-hour cook after flight. And so the reason why we did that is because we're going to be using that data later to do corrections. And then the second step was we set ground control, 15 of the points across the site. And as you can see, we used a consistent style, kind of old school, but it works. It's an L shape. You mark the center of the L. That way, when I go and do the marking, I find that middle as best I can, and that's what drives that accuracy. And then, of course, once all that's done, so you have your base and your ground control set, right? Those are first two steps before you get the drone in the air. Then we start the drone operation. For this particular project, used a Phantom 4 RTK. It did not use the base that it comes with. And the reason why is because we have other sources available to us to create that accuracy. So, and again, that's a question that you may want to ask, is why I didn't use the base. We can elaborate on that later. But again, to arrive at that accuracy, there are different ways to do that. And so that's the thing that I chose to do. So once we were done, I checked all the images to make sure that I got the coverage that I wanted. Very important to do that, otherwise you'd make a second trip. And with the Rhinex file that I got off the base and the observation file that comes off the UAV, you're able to now correct the images to get that principal point that Phil talked about tighter, so that average principal point position across this entire surface is now probably living within a decimeter box instead of a couple meters. And Phil even touched on that too, to where, you know, with the standard GPS or GNSS, autonomous mode is going to give you a lot of drift. That's why we're doing all of this. And a two-pronged approach is to use like a system like Cloud PPK in this case, and couple that with really good ground control. Now we're able to really achieve amazing accuracy. And then the final method is to run the stitch. And I did that using Pix4D, and I got the 15 GCPs. I was able to mark them all very successfully. I got about 8 or 9 per image, or I'm sorry, 8 or 9 marked on images. That's good. It allows the thing to go find these images, find those positions and that pattern, and then really dial it in. So these are the results. Very, very happy with the results. I'm actually was blown away at the accuracy, given the size of the site, and just with 15 GCPs. It actually came out to be about 2/10 horizontal. That's pretty average, right? About 2.4 inches of error you're going to get horizontally, and a lot of that has to do with GSD. And then average about 3/10 on vertical. Again, you're going to see that with vertical versus horizontal accuracy. And so if we were to go across the whole site, we would have an average of this. Keep in mind that it's going to be better as you get closer to a GCP. We totaled a little 121 million colorized points. That's pretty amazing, right? Compared to what, 20,000 points that you would get doing a survey. We're measuring, we're not interpolating. That's an important thing about all of this, is we actually measured. And so you get just so much more rich data. A side effect of all of this was we got 5 centimeter resolution RGB imagery that was tiled out, so that when the CAD operator went in to do the digitizing, it was a lot more efficient to have tiles versus a whole large GeoTIFF, which I think was somewhere in the realm of 3.5 gigabytes. Again, AutoCAD just chokes on that, so the tiles are really handy for when you're moving around. It doesn't load them all at once. And then lastly, we were able to link this whole model to a local coordinate system with a scale factor that was determined by the surveyor. And again, that's another thing that is important, is we can do grid and ground. And if you want to ask that question, please do, because we will be able to help guide you if you have these questions. And then finally, Everybody wants to know what the money looks like, because again, what are we trying to achieve? We're trying to achieve efficiency. And if we can save money, that's fantastic. And so if you look at this, 27 to 30 days to actually get a deliverable out. And this was all based on the proposal for the topo survey. $20,500 was about the rough cost there. Swing it around, look at what the UAV survey cost was, $7,800, right? 5 days to get to the deliverable. That's a 62% reduction in project cost.
That's pretty amazing, man.
So you tell me, which is the clear winner here?
Yeah.
And so I'm really glad that I was able to do this and show you guys, because this is where, like, a simple photogrammetry drone, not simple, I hate to use that word, but affordable, very capable system can achieve the same result, if not better, for a fraction of the price.
Yeah, I mean, and that's kind of the
Thank you
story
very
we
much.
like to tell,
Without
right,
further
Chris?
ado, we'll move on to Chris Kelly.
Can you guys hear me okay?
Yeah, Phil, we got you loud and clear.
All right, cool. Yeah, I mean, I was just saying, I mean, thanks, Chris, for that. I mean, that's really the story we like to tell. This is a good example. I like that you put the cost difference in there. How many acres was this, Chris Rice?
230.
230. So, I mean, yeah, I mean, and as we go up, right? I mean, and if you guys saw Jay Haskamp's study, it's also on our YouTube channel, definitely worth checking out, where it really compares, traditional survey methods, not only with photogrammetry UAS, but LiDAR UAS that we'll talk about on May 7th, and then even vehicle-based LiDAR, and really how these different, pieces come together and technologies and what they may be used for. Photogrammetry definitely has its place for a reason, and the cost savings that we can get, especially if you're looking for something like 5 centimeter resolution, pretty available to achieve that. And this is just one example. I mean, we could go all day. I mean, there's surveys that we've done that are 1,000 acres that you'd see, and exponentially it changes as you get larger and larger. So we're going to move over to Chris Kelly for a moment to talk about diversion dam that he mapped amongst some pretty high trees out there. Chris, why don't you tell us about that?
Yeah, hey, thanks, Phil. That's a good topic that you had there about the cost savings, and I'm going to kind of go over that with this project that I had. To those of you who are not familiar, the Northern Washington Cascade Mountains, pretty steep terrain changes out there. Some pretty high vegetation. I couldn't think of another place in America that is more difficult to survey in. So they had hired me to come in and just perform some UAS services for the survey team. So like I have on my slide here, we had a terrain shift of about plus or minus 500 feet with the vegetation growth over 100. So obviously it was a very difficult area to fly in. I'm not sure how many of you are familiar with Pix4D, but if you look there on my lower right screen, that section is actually a profile looking forward. So each of those green tracks is actually where the drone was flying. So what I used here was terrain following. We kind of went over that earlier, which, I think Phil had touched on that quite a bit about conserving GSD. For this instance, we're doing that as well as keeping the drone in track so that we don't run into any issues as we move up the slope. This entire project was a construction progression, so it's still going on. It's a work in progress. Yeah, that's fine, Phil. You can just go to the next slide, please. Okay, so I just want to touch base on how I did this. There's a few different ways to skin the cat, I guess, and I think that for me, it was a little bit easier on this site to use what's called propeller arrow points. And to those of you who are not familiar with these, what they're doing is they're logging GPS data. So they act as an aerial target. If you look down there in the lower left and on the right, that's what the actual target looks like. They show up pretty well in the photogrammetry. They're solar powered, so you shouldn't have to worry about the battery dying on you. Usually I charge them a day before, and I just let them run. You have to let them run for about 45 minutes. They're collecting static GPS data over time. So the longer they're on, the better your solution is going to be in the end. For this, it made it a lot easier for me, instead of having a surveyor go out there and, you know, find each individual point. Now, I mean, it really just depends on the mission, and I think that's really what I want to get at here. This just made sense. So kind of got a little bit of a map up there in the upper right on where I placed these out. I actually had a couple more just across the river. What you're trying to get is triangulation here. So laid these out, got ready to fly, and go ahead and go to the next slide, please. And just for everybody's awareness, I was actually using a DJI Matrice 210. I had the X7 mounted on that. That was one of the cameras that Phil showed earlier, one of the main RGBs. The difference here between that and the Phantom 4, for the sensor at least, is the higher resolution, which gives you a bit of an advantage so you can fly higher. So this was actually a really good opportunity for me because obviously you saw with the slope and the terrain following that I had to do, the higher the better. So I use a third-party app for this. You can still use DJI Pilot. I find this app called Map Pilot to be pretty significant in my line of work. I like to use it quite a bit. They already have the DEM labeled in there, so you just apply it. You can see right there where the yellow line is. That would actually be the takeoff altitude. The red and the green would actually be the actual terrain, and then the blue being the flight height. So it's following the terrain all the way through, and that's just a side profile of what you would see over there on the right, the actual mission. So it's mission planning software. It just details everything a little bit easier for a new user, I think. So I tend to use this quite a bit. I think it's a great software to use for this certain drone. So
yeah,
next
Chris,
slide.
and just to interject there, I mean, that's I don't mind giving a little plug. I think Map Pilot, it's a company called Maps Made Easy. We use this a lot. One of the benefits that it offers, as Chris mentioned, is this terrain following. It's something that DJI has not actually started to do yet. And one of the benefits of using the M210 is that you're able to use third-party software, whereas with the Phantom 4 RTK, it's really just available with the embedded controller, and it does not have terrain following yet. So as far as safety and maintaining that accurate GSD, we don't mind giving a little plug to Maps Made Easy. We use it. Nathan uses it with LiDAR. I use it with M210. Chris uses it with M210. As you can see, we're very passionate about this. It's a great piece of software. And I think, correct me if I'm wrong, Chris, but it's available on the Apple App Store. Is that correct?
Yeah, Phil. You'd have to you download it through Apple. We've tested it on Droid devices. It doesn't seem to work very well. So yeah, if you're going to do this, I'd get an iPad and run it through the App Store.
Cool.
I believe it's $30 to get the app and then $30 for the lifetime membership. So yeah, good call on that. I think that, you know, the Phantom can actually do some terrain following. It's just a bit more tricky to get it set up. So in this instance, you know, I just think that Map Pilot is easier for the end user, especially if you're out in the field and you just don't have time to set something up. So good call on that one. Thanks, man. All right. So one thing with the X7 that we found out over the time of surveying with these is that we had a little bit of distortion, some whiteout in a lot of our imagery. So while you're processing this, you can actually lose data. So this lens needs to be calibrated each time. It'll actually let you know as soon as you turn it on that it needs to be calibrated. What we try to tell everybody is that you should calibrate it with each mission. And really that has to do with the light of day. So if there's any kind of environmental change, you should probably recalibrate. It's not really that hard of a process. It's going to save you in the end. There's an extra step here. I'm just going to go through it real quick. I know we're kind of limited on time, but what I do, because I'm using the Map Pilot on the iOS or the iPad, I have to swap out with the Crystal Sky because you have to calibrate the lens through Crystal Sky, which is that DJI Android-based interface. So I fly up once with the Crystal Sky and I get to altitude. I find a high contrast area. You can see in that image on the left is very blurry. So you find a high contrast area, and then you just calibrate the lens. And it auto does it for you. You can see on the right what the focus will do for that. So after that, I land. I unplug the Crystal Sky and then plug the iPad back in and go to my Map Pilot. And I've already got my mission plan by that point. Next slide, please. Thanks. All right, so overall, this is the mosaic that I came up with at the end. This is about a 10-acre survey through mountainous terrain, again, heavy equipment moving raw material. If you look at that mosaic, there's sort of a white area right there in the middle. That's just a dirt path. You know, I think you remember from when I had the arrow points down, that was all tree cover before. So they've logged all of this. It's muddy, they're moving material all the time. So it's just not the easiest place to access by any means. And that's why UAS came in, and it really helped them out in the long run. We were able to actually pull off a 1.8 centimeter GSD point cloud, and we got similar results to what Chris had as well. So, you know, I think in the end, the results were so good, these guys just kept on calling me out to come back and do more. And I think that, you know, this is a great scenario on how drones can be used for places that are just hard to access. And you know, there's all kinds of uses for these, but when you start looking at it like this, it's all about finding the right tool for the right job, and that's kind of what we started out with. So I just wanted to share that with you guys and my experience, and yeah.
Yeah, thanks, Chris, man. That was awesome. Definitely a unique job, and you know, from feedlot to this, it's about as different as it can be, but just showing kind of the broad spectrum of applications that we can utilize UAS for. So awesome. And then finally, we're going to talk to Mike Clarenbeek, and he's going to talk a little bit about public safety and some accident reconstruction he did.
Hey guys, so obviously being able to measure is a very valuable tool, and the way that people have been using it in public safety is to measure things in regards to accident scenes, any investigation. It's a great way of documenting everything and then going back after the fact. So if you missed a measurement, if something that you wanted to look over and you wanted to go back and see where it was laying, it pretty much documents the whole scene. So it's very valuable in the fact that you're not going to lose any data. You're going to hang on to it, and you're going to be able to reference it. And we're finding it being used in the court more and more, which is really, really interesting. So you can see some of the benefits there. It's inexpensive in comparison to some of the previous tactics used for crime reconstruction and documentation. It's quite a bit cheaper. It's faster. So to fly the mission and be on site, it takes less time than traditionally measuring things. And again, you have all the advantages of having all that information there that you can always access. It's very versatile. So you know, you're not limited to just one method now. You could use an old method, but now you have this method to being a faster way of collecting data. You don't have to necessarily close down a highway or a street or something like that. Or if you do have to close it down, say it's a busy road and you have to overfly it, you only have to stop traffic for a very short period of time. So you're not closing that down for longer than you really need to. This is the fastest way to keep a road open, which everybody's happier if they don't have to do a detour or get stuck in traffic. Again, so using those measurements, you can see in the example picture I have there, there's these little orange markers there. Again, you can go into each marker and you can measure from point A to B. So it's pretty straightforward. If you wanted to measure the tracks there, it's just an example I did there was how long is the track. You can measure slopes. So again, you can very easily, using traditional methods, calculate kind of the velocity of an object, how fast somebody was going down the road, what angle. You can also do fly-through videos. So if you wanted to see what did it look like when the driver was sitting in the car, you can go through this scene that you just reconstructed and see, hey, was there a blind spot? Was there a tree blocking something? So it picks all that information up that normally you would not normally have unless you used, you know, just a video camera and drove through it. So I think that's, here's a couple other things you can export. So this is Pix4D React. So the first thing I was talking about was just Mapper. And with Mapper, you're able to reconstruct everything in 3 dimensions. With React, it's kind of a quick response. For search and rescue, you could do accidents, but you're only going to get the 2D, so the 2D measurements. But what it allows you to do is basically get on scene and create a better situation awareness. So if you're doing a search and rescue, hey, we launched the drone, now we have a map of the whole area. We can make annotations on there. We can do some basic measurements. It's not going to be quite as precise as it is in Mapper, but it's still pretty good. So if you needed a good idea, like how long is this road to get in there, or how big an area do we need to search, you can do those measurements really quick and easy. And then you can make reports really quick too. So if you need to print off some documents for volunteer search and rescuers, they're using it in a way that say, hey, search this area. This is things that we see in this area. Please find out what they exactly are. So that data allows them to make better decisions. And it's just another tool in relation to photogrammetry that has really changed the way people approach search and rescue operations now.
Awesome, Mike. With all of these guys, one of the things I liked and that we didn't really cover, I mean, photogrammetry is a pretty deep science. There's a lot of things. I wanted to just kind of spend a brief time talking about how we apply it along with some of the history. But, I think that there's much more to go on this. There's much more to be filled in. I just want to thank you guys for joining us. As far as, coming up, again, this is our UAS team, everybody that was on here today. There you go. So just to remind you guys, we had a couple of webinars. Today was the third. To update the slide that we had previous, we're going to be doing our UAS LiDAR in 2 weeks from now on May 7th. So don't miss that. And Nathan, if you have a few minutes, I mean, it might be cool to kind of open up the conversation and talk about some of these questions or things that you thought were pretty interesting.
Well, one of the questions that just came in is, does Frontier Precision offer any type of classes for people that want to learn more about photogrammetry? And the answer to that is yes. We haven't been hosting in-person classes recently, although we plan on hosting quite a few classes coming up here. So we do host a one-day Part 107 training class. So that's to prepare you for your Part 107 certification. We also host a 1 or 2 day Pix4D class. So in this case, we focus on Pix4D as the photogrammetry software. And afterwards, going through that for 2 days, you'll be good to go for processing drone data.
Well, as always, guys, thanks for joining us. It's definitely been educational here. Thank you guys, all of my cohorts at UAS, Frontier Precision across the nation. Stay tuned for our LiDAR in a couple of weeks. And that's not where we'll stop. We're going to be doing webinars like this on a regular basis. And tune in. And thanks again for joining. And we'll see you in a couple of weeks.